Today you will apply the fundamental theorem of algebra to polynomial functions. So with the fundamental theorem of algebra, notice this is what it says. If a polynomial of degree at least 1, then p of x equals 0 has exactly n roots. Meaning if it's a linear a polynomial, there's 1 root. If it's quadratic, there are 2. If it's cubed, there are 3. Including multiple and complex zeros. So notice the first parabola, we have 2 real zeros because there are 2 locations in which our graph crosses the x-axis. The one in the middle has 1 real 0, but it's called a double solution because it just swoops down, touches the x-axis, and then turns back around. And then in the third picture, there are no real zeros because the parabola does not cross the x-axis. Okay, so our same examples as before, so we're going to find our possible zeros first. Okay, so possible and remember we're going to take the factors of the constant divided by the factors of the leading coefficient. So that leaves us with possible zeros plus minus 1, plus minus 2, plus minus 4. Now, remember we're going to test possible zeros. Remember we can use Descartes' rule of signs to get some hints. Okay, so what that means is I'm going to look for sign changes. Notice we go from a positive to a negative, then we go from a negative to a positive to a negative, and a negative to a positive. Okay? 1, 2, 3, 4. Okay, so what that means is if we have 4 sign changes, that means we have 4, 2, or no positive zeros. Okay, so remember to find the negative sign changes, you're just going to plug a negative x in for the x. So notice when we plug negative x in for the equation, we do only have 1 sign change. So that means 1 negative root. So notice what we're going to do is we're going to use those 4, 2, or 0 positive zeros and 1 negative 0 to find zeros. And it just so happens that 1 does work. So when we do 1 for synthetic division, notice we're not missing any terms, so we're just going to drop those coefficients down. And notice we have no remainder. Okay, so the next thing we can do is we can write it in factored form just like we would before. We'll have x minus 1. If you take an x to the 5th and divide by an x to the 1st, that does become x to the 4th. And x 4th minus 3x squared minus 4 does end up factoring. Okay. So we'll have x squared and x squared Factors of 4 that give us -3 are -4 and +1. And then our zeros, x equals 1, x equals plus or minus 2, and x equals plus or minus I. Okay, so remember our degree is 5. We should have 5 solutions, which we do. Now real quick, let's go back up to the top. Instead of doing a whole bunch of algebra to see if you get 0 on the right side, you can do something with your graphing calculator if you have one. So what you'll do is you'll type the equation into the y equals button. You'll go to the home screen, which you would push second mode, and then find the green alpha and then the trace, which is up at the top right. You'll put like 1 in for the parentheses, so you'll have a y1 on your home screen, right? It'll look like y1. You'll put in parentheses 1, and then you'll push enter. If that equals 0, then it is a solution. The other thing you could do y1, 2, because it's another possible 0, and then push enter, and it would give you to see if that equals 0 or a solution. Okay? What I want you to do now is to try the example you tried. Okay, so this one was a little bit more of a complex problem. So notice that because there is no constant, 0 is the constant. So 0 is definitely a 0. And notice in the original polynomial, there are 2 sign changes, so that means 2 or no positive real zeros. If you plug -x in for the polynomial, you do get 1 sign change, which means there's 1 -0. So since we know 0 is already definitely going to work, notice that we do have a no remainder here. And when we refactor it, we do have x times x cubed plus 2x squared minus 13x plus 10. Well, because we can't factor that guy, we have to go through the process all over again. So of our reduced polynomial, our possible zeros are plus minus 1, plus minus 2, plus minus 5, plus minus 10. And there are 2 sign changes, so that means there are 2 or no positive real zeros as verified up above. So we're going to try 1, why not? And it does actually end up working. Notice that there is no remainder again. And then when we write our factored form, please do not forget the 0 and also that 1 in our factored form that we have here. And then the resulting trinomial x squared plus 3x minus 10, which does factor to x plus 5, x minus 2. Therefore, our 4 solutions are 0, 1, -5, and 2, which verifies that we have a degree of 4. We should have 4 answers. We are good. Let's look at another one. Okay, so we're going to find all the possible zeros again. We're going to follow the same exact steps we did earlier. So the first step, we have our possible zeros. Six is our constant, and 2 is our leading coefficient. So we'll do the factors of 6 on the numerator. So 1, 2, 3, and 6, 2 in the denominator. Okay, so these gives us zeros plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus 1/2, and plus minus 3/2. Okay, and so now we're going to use Descartes' rule of signs to figure out how many possible sign changes we have. So let's take a look. We go from positive to negative, and that is the only one that I see. So for step 2, we have 1 sign change. So that means 1 positive 0. Let's find p of -x. And notice we have 1 sign change, so we also have 1 negative root. So we have 1 positive, 1 negative. Okay, so now we can find possible zeros. Take a second and see if you can find one. I actually found one to be 2. So let's try it. Let's see, our coefficients are 2, -3, 0 for that x squared, -1, and -6. Okay, so we're going to drop down the 2. -1 plus 4 is 3. And guess what? It worked. So when we write it in factored form, don't forget the x minus 2 because we divided by a positive 2. And then when we take an x to the 4th and divide by an x to the 1st, we do have 2x cubed minus or plus x squared plus 2x plus 3. Okay. And did anyone find a different 0? Well, because this guy isn't going to factor again, let's see if we can find the -0. Let's try -1. Drop down the reduced coefficients. And -2, 1 plus -2 is -1. -1 times -1 is 1, 3, -3. And guess what? It worked. So remember our factored form. We had the x minus 2. Now we have an x plus 1. If I take an x to the 1st and divide into x cubed, we do have 2x squared minus x plus 3. Okay, so we have to solve that resulting quadratic. I know how a lot of you guys feel about factoring when the leading coefficient is not 1. So remember, you can do quad formula if it would put your mind at ease, or you can try and factor it. Let's see here. I'm going to do quadratic formula. So I'm going to do my discriminant. So we'll do -1 squared minus 4 times 2 times 3. And that gives us 1 minus 24, which is -23. Or x equals the opposite of b, so 1 plus minus the square root of -23 is I, square root 23, over 2 times a, or 2 times 2, which is 4. So we have two solutions here. We have this guy, and we have this guy. Okay, so if we go and look up at our original problem, notice that we had a degree of 4. Do we have 4 solutions? We have 1, 2, 3, 4. So yes, we do. So we're good. I want you to take a few minutes and see if you can figure out the example you tried. Okay, so this one was really not that bad. So notice our possible zeros are plus minus 1, plus minus 3, plus minus 5, and plus minus 15. Notice we had 2 sign changes, so we had 2 or no positive real zeros. And when we did p of -x, we only had 1 sign change, so that means only 1 negative real zero. And when we did our process of elimination, we decided to go with the negative zeros because I know that is definite. And -3 did end up working. So remember, when we write our factored form, we drop down that x plus 3, and then we write x squared minus 2x plus 5, which no factors of 5 add to give us -2. So that means we have to do quadratic formula. We do get 1 plus minus 2i. Now, notice that we do have 3 solutions. Our degree is 3, so we are good. So in our next type of problem, this time we know that x equals square root 2 is a 0 of the polynomial, and we're going to find all the factors and the zeros, okay? So the first thing that I would do, if I know x equals square root 2 is a 0, I know I can use that with synthetic division. Okay, so if I know x equals the square root of 2, I'm going to put some square root of 2 in my box. Drop down your coefficients. And notice we're not missing any placeholders, so that's good. Okay, so we know 1 times square root 2 is square root 2. 4 plus square root 2 is 4 plus square root 2. Now this is where it would be good to have some scratch paper or off to the side, because we know that we'll have to do square root 2 times 4 plus square root 2. Right? I have to take this guy and multiply it with what's in the box. So let's see, we'll have 4 square root 2, and then square root 2 times square root 2 is 2. Okay. Okay, so now we're going to add down. So we know we'll have the 4 square root 2, and we'll have minus 5. Okay, so we're going to multiply that, right? We're going to take that times what's in the box. So let's see, we'll have square root 2 times 4 square root 2 minus 5. Okay, so we'll have 4 times square root 2 times square root 2, which is 2, so we'll have 8 minus 5 square root 2. And when we add down, the 8's cancel out, and we just have minus negative 5. Oh my gosh, my handwriting is not the best today. Okay, and now what we'll do is we'll take that and we'll multiply it again. So square root 2 times negative 5 square root 2. Well, we'll have square root 2 times square root 2, which is 2, times negative 5 is negative 10. And guess what? That worked. Well, what do you know about square roots? They come in complex pairs. Okay, so that means we can also do the same thing with negative square root 2. Right? Conjugates always come in pairs. So we're going to drop down our reduced coefficients. And do the process all over again. We know 1 times negative square root 2 is negative square root 2. And the root 2's cancel out, so we're just left with 4. We'll have 4, negative 4 square root 2. The 4 square root 2's cancel out, and we just have negative 5. Negative 5 times negative square root 2 is positive 5 square root 2, which gives us 0. Wow, look at that. So our factored form, we know we had x minus square root 2 from the first one. We'll have x plus square root 2 from the one we just found. And then if I take an x to the 4th, meaning I took an x to the 4th and I had divided it once and twice, that means my new degree is x to the 2nd plus 4x minus 5. Now, do we have factors of negative 5 that add to give us 4? Yes. Okay, so we're going to copy down our polynomial. Okay, factors of 5 that add to give us 4 are positive 5 and negative 1. And then we have our zeros. We have plus or minus the square root of 2, negative 5, and 1. And notice we have a degree of 4. We have 4 solutions. Done. Now let's look at another one. This time we know that negative 4i is the 0 of the polynomial, and we're going to find all of the factors in zeros. Okay? So, there are a couple ways we can approach this one. This one is slightly different. Notice that there is no constant, so if it were me, I would probably go ahead and use 0, because I know that is a solution because everything has an x in common. So if we do 0, we'll have 1, negative 6, 16, negative 96. We have x to the first, which is 0, and we have our constant, which is 0. Okay, so let's think. This is now x to the 4th. This is negative 6x cubed. This is 16x squared. and this is negative 96x plus 0. So there's still an x in common. I would divide it by 0 again. Okay, so this now is x cubed minus 6x squared plus 16x minus 96. And we know that we have negative 4i, so we're going to do that one. Okay, now again, you might need to work off to the side, because notice we are going to have some complex numbers. Let's see, negative 6 minus 4i does nothing. And then if we take negative 6 times negative 6 minus 4i times negative 4i, that gives us, let's see, positive 24i plus 16i squared, which is minus 16. So 24i minus 16. 16's cancel out, so we just have 24i. And 24i times negative 4i is negative 96i squared, which becomes positive 96. Okay, so just like with i's, just like we did a long time ago, its conjugate is also a 0. I have to work off to the left, sorry. So we're going to do 4i, and then we're going to drop down our coefficients. So we'll have 1 times 4i is 4i. 4i's cancel out, we'll have negative 6. Negative 6 times 4i is negative 24i, and then the i's cancel out again. Awesome. Okay, so let's write our factored form. So we know we have an x, we have an x, we have an x minus 4i, we have an x plus 4i, and we have an x minus 6. Okay. Notice that our zeros then are 0 plus minus 4i. And 6. Now, one thing I forgot to include from up above. See how our problem says find all of the factors in zeros? Well, we just found all the zeros. To find all the factors, what we would have to do is we would have to write it out like we would see in factored form. So we'll have x squared. We know x minus 4 times x plus 4 is x squared plus 16. If you need to multiply that all off to the side, you can. Here is our formal factored form, which means we need to go back up to the previous example and do the same thing. Okay, so for our factored form, let me zoom in a little for this guy. We have to multiply, we have to multiply these guys out over here. Okay. So let's see, x minus square root 2 times x plus square root 2. Ugh, handwriting is horrible. Okay, let's see, x squared minus x square root 2 plus x square root 2 minus 2. These cancel out. So our factored form, I'll change my color again. We'll have x squared minus 2 times x plus 5. Let's see, x minus 1. Okay, so this is your factored form for this guy. And finally, here's some nice hints and tricks. Okay, so remember these are equivalent ways to state the fundamental theorem of algebra. You can use any one of these statements to prove the others. So remember, for each polynomial equation where the degree is at least 1, has exactly n roots, including multiple and complex roots. Every polynomial degree of n is at least 1 has n linear factors. And every polynomial function of degree of n is at least 1 has at least one complex zero, meaning 1 or more. And that's it. That's all she wrote.